All right, today we're going to be solving exponential equations. As we were working with logarithmic equations and logarithmic expressions, one of the questions that's always been in the back of our heads is, why do we do this? And the reason why we use logs is so that we can solve exponential equation. Remember, an exponential equation is an equation in which the variable, or whatever letter we're trying to solve for, in most cases x, occurs as the exponent. And when the variable is in the exponent, there are different methods that we could solve. One of them, which will always work, is taking logs, is using the log of both sides. But there's other methods that might be a little bit quicker. And we've done some of these before, where if our bases are the same, then our exponents must be equal. So if b is a positive number other than 1, then b to the x equals b to the y if and only if x equals y. So whatever the exponents are would be equal. And it might just be more than just, x equals 3. It could be a whole expression. So here, if 5 to the x equals 5 to the 4th, then x must equal 4. And if x equals 4, then 5 to the x equals 5 to the 4th. So down here, we can use this. We have 64 to the x power equals 16 to the x plus 1 power. Now, can we rewrite this as any other base? Well, we know that 4 squared is 16, and 4 to the third is 64. So we can write this as 4 to the third to the x power equals 4 squared to the x plus 1 power. Because 64 is equal to 4 to the third, and 16 is equal to 4 squared. And now remember, when we have a power raised to a power, we multiply the powers. We multiply those exponents. So this becomes 4 to the 3x equals 4 to the 2x plus 2, because we've got to multiply both of these things by 2. And now, since the bases are equal, that means the exponents must be equal as well. And when we subtract 2x from both sides, we get x equals 2. And we could check that and plug it back in if we would like. So if we can change our bases around, that would make life a lot easier. Letter B over here, in order to solve this, we need to get this part by itself right here, whatever our base raised to the exponent is. So let's subtract 8 from both sides. So we have 6 times e to the 0.25x equals 12. Then we're going to divide both sides by 6. So we have e raised to the 0.25x power equals 2. From this step right here, we're going to take the natural log of both sides, or the ln. And the reason we're going to do that is because on the left, we know that the ln of e kind of just cancels out. So on the left side, we're left with 0.025x. Technically, you could take the log of both sides with any number as your base, but I always like to do the base of whatever our exponent is. Now our calculator, we're going to type in the ln, or natural log of 2. And we get 0.69. And then we'll divide both sides by 0.025. So 0.69 divided by 0.025. And we get 27.6. So we're going to be using this log feature, the log buttons in our calculator, frequently. Now, letter C, I'm going to show you two different ways you could do this. They both work. The first way is to change this from exponent to log form. We already have our base by itself. So we could say log base 6 of 27 equals x. And then we know we could type this into our calculator. Okay, that's one way of doing it. Okay. Another way of doing it is taking the log base 6 of both sides. Now watch what happens when we do log base 6 of both sides. So log base 6 of 6 raised to the x power equals log base 6 of 27. We know that log base 6 of 6 cancels, and we're left with x equals log base 6 of 27, which is exactly what we had over here. So we can do either way. We're going to get the same answer. Even for letter B, at this point right here, we could have changed this to log form and did log base e of 2 equals 0.25x. And look, we have that right here, ln of 2, log base e is the ln or natural log. So either way, you're going to get the exact same answer. I go back and forth on which way I'm going to use, just depending on the numbers involved, to see which way is a little bit more efficient. So x will equal, type this into the calculator, 1.84. Okay, so let's look at the next page. So I'm going to do these three as well. So we'll subtract 2 from both sides. We get 3e raised to the 0.5x equals 3. Divide both sides by 3. We get e raised to the 0.5x equals 1. And now from this point, we can take the ln, or the natural log, of both sides, or switch this to a logarithmic form. So we have the ln of e, 0.5x equals the ln of 1. The ln of 1, I believe, is 0. Yep, 0. So these cancel, we're left with 0.5x equals 0. And when we divide both sides by 0.5, we get x equals 0. Now, one of the things I do like to do if I'm using my calculator is that you can plug in your x value. So 3 times e raised to the 0.5 times 0 power plus 2, and we should get 5. So I'm confident that we've done this correctly. Letter E over here, I'm going to switch this to log base 5 of 72 equals x, my exponent. And then I'm going to type this into the calculator. Log base 5, 72, and we get 2.66. And then the last one here, we could do this one the same way we did the very first one, where we rewrote it as different bases, and that will still work. But another way to do it is to take the log of both sides. So I'm going to do this problem that way. Yes, it's going to take a little bit longer than this problem up here, but what if you didn't realize that 4 to the third was 64? I want you to still be able to solve this problem. So I'm going to take the log of both sides, and it could be any log. It could be log base 3, it could be log base 9, it could be log base 10. So I'm going to do log base 3, and the reason why I'm going to do log base 3 is because I have a 3 right here. So this 3 is right there, raised to the 7x minus 3 power. Because yes, I can't take the log of 3 on the left side and the log of 9 on the other side. So I just pick 1, because that will then allow me to cancel at least one side. And I usually pick the log that has the most stuff. So like in this one, I probably would have did log base 16 on both sides because that exponent had more things in it. This one, I did 3 because it had more stuff in it. So on the left side, this simplifies to, those go away to 7x minus 3 equals, well, remember one of the properties of logs is that we can take this exponent and put it out in front. So it's going to be 2x times log base 3 of 9. But we can type this into the calculator, log base 3 of 9. Log base 3 of 9, and we get 2. So 7x minus 3 equals 2x times 2, or 4x. So 7x minus 3 equals 4x. I'm going to subtract 7x from both sides. So we get negative 3 equals negative 3x. So we get x equals positive 1. And again, because of all this math going on, I might still go up here to my original equation and say, let's just double check that x equals 1. So 3 raised to the 7 times 1 power minus 3, 81. 9 raised to the 2 times 1 power is also 81. So I'm confident that that is our answer. So yes, you could still take the log of both sides and you get this mess over here, which again does work. You can still do this. Recognizing the powers was just much faster to do this. Now the last one is a word problem here. So Newton's law of cooling is a way to tell or to work with temperatures and seeing how often or how quickly an object cools depending on its outside environment. For example, when you take a dish out of the oven and you let it cool before eating it, or you pour hot coffee and you have to let it cool before drinking, the way that those things cool is a function of Newton's law of cooling. So we have this equation here, which if you ever need it, I will give you this equation. So it says hot chocolate that has been heated to 9 degrees Celsius is poured into a mug and placed on a table in a room temperature of 20 degrees Celsius. If R is 0.145, when the time t is measured in minutes, how long will it take for the hot chocolate to cool to a temperature of 30 degrees, round to the nearest minute? So we have some things that we have to plug in. Whoops. We want the final temperature to be 30. So that's going to be T. So 30 equals T naught. T naught is the initial temperature. So right there, that is 90 degrees minus TR. TR is the surrounding temperature. So that means the starting temperature right here is 20 degrees. So anytime we see a TR, because we have one here and here, we're going to replace that with 20. Then e raised to the negative RT power. R is 0.145, so negative 0.145 times t, because that's what our exponent is, plus another 20 degrees, because that's what TR is. So now we're going to simplify this. Subtract 20 from both sides. So we get 10 is equal to 70 e to the negative 0.145 t power. Divide both sides by 70. So 10 divided by 70. It was 0.14, 0.14 equals e raised to the negative 0.145 t. So at this point, I'm going to take the ln of both sides. See how much room do I have? Okay, I have enough room down here. So the ln, or natural log of 0.14, equals the ln of e to the negative 0.145 t power. The right side is going to be negative 0.145 t. The left side is going to be the ln of the ln of 0.14, and we get negative 1.97. So then we do negative 1.97 divided by negative 0.145. And we get 13.59. 13.59, I'm sorry, 13.59. And what are the units? Minutes. So this is used, this Newton's law of cooling is also used to determine, how long ago someone died based on their internal temperature and the temperature of the surrounding area. So there is usefulness to this. So thank you for watching the video. Hopefully that this was a good video to see why we use logarithmic equations or logarithmic functions to help us solve these exponential equations. So thanks for watching. Make sure to like and subscribe.